Welcome to gemchem. Now today's topic of discussion is isomerism. This is the part 8 video. Already 7 videos are uploaded in channel. You can watch it. I will give the link in the description box as well as the I button present about this video. So let us start. So in the isomerism case, there are this broad division of isomers. One part is structural, another part is stereoisomerism. So structural isomers have same molecular formula but different molecular structures. For example, in organic chemistry we know that ether and alcohol, that is CH3OCH3 and CH3CH2OH. So here there is a differentiation in the structure. As a result, these are structural isomers. And in the second case we have stereoisomers. This has not only same formula but also has same connectivity among their atoms, but the spatial arrangements of those atoms are different. Now if you can focus here, for structural we have ionization isomer, linkage isomer and coordination isomer, whereas for stereoisomerism we are going to have geometrical isomer and optical isomer. So what are geometrical isomers? They have different spatial orientations and this results in different geometries. And this geometrical isomers has certain symmetries in them, that is elements of symmetry, which we have already discussed in the channel. You can watch the video. I will give the link in the description box as well as the I button present about this video. And optical isomers have same geometrical parameters but are related as non-superimposable mirror images. So we can say that these molecules are chiral. So this optical isomers generally get their names because they are able to rotate the plane polarized light beam to the left or to the right. And the structural isomers is the first part which we are going to discuss in details. So first is ionization isomers. Here the ligands present inside the coordination sphere sometimes exchange their places with the ligands present within the coordination sphere. And these isomers are specially named like this because when they are dissolved in water, you are going to get different types of ions from them. So first see this example. So when you dissolve it in water, you are going to get this part of platinum complex as positive charge and SO2- as negative charged ion. Whereas in this case you can see sulfate has come inside, one of the chlorido group has gone outside. So here you are going to get this full part as cation, whereas Cl- as anion. So solutions of both of these are neutral, but the ions which you are going to get after the reaction or the after dissolution in the water will be different. Similarly, this is another example, and from here you can see that chlorine has exchanged its place with water. So the subcategory of ionization isomer can also be called as hydrate isomerism. So here what happens is that the water exchanges its place from inside of the coordination sphere to outside. Now we shift for our next type of isomer, which is linkage isomer. So from the word link only you can understand that there will be a variety of linkage or linking between the two atoms. So this is mainly concerned with our ambidentate ligand. So linkage isomers can exist when one or more ambidentate ligands is bonded to a metal ion. So the ambidentate ligands which we have already discussed, you have known and seen it. So if you have not seen it, you can watch the video. I will give the link in the description box as well as the I button present above this video. So the ambidentate ligands are as follows, like NCS, thiocyanate, or you have cyanide, or you have nitro. So these are the certain examples. Now so we can say that these exist when one or more ambidentate ligands are bonded to the metal ion, and example of this is, you can see here NCS is the connection, N is the connection, whereas SCN, in this case sulfur, is the connection. We have already seen the nomenclature of ambidentate ligand also, so this will be helpful for you. Now we can see another example where nitro group is present and here nitrito group is present. So these are the two types of ambidentate ligand and they show linkage isomers. Third one is coordination isomer. So this involves ligand exchange between the coordination spheres of two metal ions. Suppose we have a complex salt where there is two coordination spheres, that is, one is positive, one is negative. In that case, the ligands get exchanged. So we can see here our charges, this one is positive, this one is negative, this one is positive, and this one is negative. Now we are going to discuss about the stereoisomers in metal complexes. And in this case, first topic of discussion will be our square planar complex. So in general, geometrical isomers are found in square planar complex, and not usually they are optically active because there is either presence of any of the symmetry elements within the sphere. So first example is that we have a metal in between and A2 and B2, that is, there is two types of ligand present, 2 in number each. So in this case, first what you are going to do is place the metal ion in between. Then after placing the metal ion in between, try to position the hands like this. Once it is done, first position A and A opposite, and this is known as trans, as we know from our organic chemistry view. So this is trans, and if you place it side by side, that is A and A, then it becomes cis, right? So it is becoming cis. So we can see the two isomers obtained for this is, suppose you have NH3 and NH3 in the position of A and Cl as B. So this is trans platin and this is cisplatin. Now both of these should be separated. Suppose you have a mixture of these two. So how can you separate it? You can separate it by using bidentate ligand, that is bipyridine you can use. The one in which there will be color change is cis because there will be a reaction with this, whereas bidentate ligand can span in the cis position only. It cannot jump from one trans position to another, as a result of which we see in the trans platin there is no reaction taking place, whereas in the cisplatin you can see Cl minus has gone, as a result of has got attached to it, replacing the two Cl minus ions which are cis with respect to each other. Now we are going to see our next type, that is MABCD. So in this case you can see what happens is you have each of the ligand present, so fix one of its position. What you have to do is take M, fix A here. Here is B. So first you make C trans to A. Done. Next one you are going to fix A as usual, put B trans to A. And the last one which you are going to do is place the D trans to A. As a result of which you are getting 3 isomers of this one. And this is your final answer to the question of isomer for MABCD. So see here, you have an example like this where you have ammonia ligand, CH3NH2 ligand and chlorine and bromide. So this is AB are trans to each other, next one is AC is trans to each other, and the last one is AD is trans to each other. The next type is that here we are having a symmetric bidentate ligand and B2 is another one. So since it is present like this, this head on represents that it is a bidentate ligand. So we can see that for this case it does not exhibit any type of isomerism, as here the path is being locked. No trans or cis isomerism can be seen. So we can write here do not exhibit isomerism. The next one is our another bidentate ligand, but here the donor centers are different. For example, we have already seen PAP, right? So our example is this one. You can see here this is a PAP ligand. This part is trans to another one. And if you take the cis ligand, so in that case cis bonding is being seen in the another one. So this is trans isomer, this is cis isomer. So this is the molecule where it is represented platinum, PAP, twice, bracket, and here platinum is 2. Now we shift for our next type, that is Ma2 BC. So you will have AA trans to each other, then you will have cis AA. So these are the two which are being possible for this one. Next we go for symmetric bidentate ligand, but they are 2 in number. So one will be like this and no more combinations are possible, as a result of which this type of square planar complex won't exhibit any kind of isomerism. Next one is this one. Again for this one, since this part is being bonded, so as a result of which there will be no isomers seen. So we have already seen the 3 types where in the square planar complex we are unable to see any kind of isomerism. First one was this one, next was the other 2, that is this one and this one. No isomerism is being observed. Now this is the most important complex, which is a square planar complex, but still it exhibits optical activity. This is Mills-Quibell complex and this looks like this. So if you can focus here, this is your structure. So just remember, it has no plane of symmetry because all these things are placed above and below the plane. As a result, plane of symmetry is not observed and we can see optical activity in this. So this is one of the isomer, and if you reflect it using the mirror, you can get another isomer. So these are the 2 enantiomers which we obtain for Mills-Quibell complex. So in octahedral complexes, first one which we are going to deal is Ma2B4. So in that case we are having same type of 2 ligands and another type as 4 ligands. So here you can see what the difference comes is that similarly AA can be kept trans and BB can be kept trans, whereas AA can be kept cis. As a result, BB will come also as cis. So these are the 2 isomers, trans isomer and cis isomer. So in case of trans isomer, you can see there is a presence of sigma plane, as a result of which this can't be optically active, whereas in case of the cis isomer also sigma plane which is passing through this chlorine, ammonia, this chlorine, amine, as well as this amine and this chlorine one. So this is the sigma plane which is passing. Similarly in this case you have in the trans isomer case I. So there is no possibility of optical isomerism. So we get geometrical isomers. Next we go for our Ma3B3. There is 2 types of ligand, 3 in number each. So from here you can see that in the first case you have a facial isomer, that is in a triangular form you are having the same ligands placed, whereas in case of the next one you can see that no such arrangement is being made. Any one vertex of the triangle is being exchanged by another ligand. So this is known as facial isomer and this is known as meridional isomer. So if we try to see the symmetry elements present here, so in the meridional isomer you can see that there is a symmetry element present which is passing through the plane like this, passing here. As a result, this sigma divides the molecule into 2 equal halves, whereas in this case here is a sigma plane which is dividing the molecule into 2 equal halves. So we can see from here that the FAC as well as MER isomer does not have any optical activity. Now we shift for the next one where we have Ma2B2 C2, that is there are 3 types of ligands. An example for this one is PtCl2 NH3 whole twice Br2. So first we are going to keep A, B and C trans to each other. As a result, we are going to get such type of isomer. Second, what we are going to do is keep A in trans position, whereas B and C will be made cis to each other. As a result, we can see CC cis and BB cis, whereas AA remains trans. Now next we are going to make the 2 C trans to each other. So here we can see C's are trans, whereas other groups becomes cis to each other. And the last one which we are going to see is CTC, where you can see the B is trans to each other, whereas others are cis. The last one will be all of them will be cis to each other. and we can say this is the isomer where all the groups are cis to each other. Now if we try to get the symmetry elements, so in this case we will have for this one sigma plane passing through this. Similarly for next one also sigma plane passing through this. Another one will be sigma plane passing through this. For this one you will have a sigma plane passing through the another one which is present here, this one and this one. And the last one, if you try to get the symmetry element, there will be no symmetry elements present in this case. As a result, we can conclude that this will show optical activity. So it will have a enantiomeric pair, which is this one, just the mirror image of this one. Now we are going for the next one, that is M, and here you have a symmetric bidentate ligand and B2. So phenanthroline twice and H2O twice in presence of Fe as metal ion. So here you can see first you have to keep them trans to each other, right? And in the second option you can keep them cis to each other. So let us find out the symmetry element. So here you can see that there is a sigma plane, whereas in the second case you are not going to get any type of symmetry element. So you can hope that it will be optically active. So here it is having an enantiomeric pair to each other, and the mirror image which you have obtained is non-superimposable to this one. Next one which we are going to deal for the octahedral complexes, one symmetrical bidentate ligand and you have B2C2, that is there are two different monodentate ligands attached to that. So example is that cobalt, ethylene diamine, Cl2 and amine ligand twice. So first you are keeping B and C cis to each other. So for that you will get this one, that is CC. So they are cis to each other. Second one is trans and cis, that is you are keeping B and B trans to each other, whereas CC in cis position. And in the next one you are keeping C and C trans, whereas B and B are kept cis to each other. As a result you are getting three combinations, TC, CT and CC, where they are cis to each other. So let us find out the symmetry elements. So in this case you can see for TC it will be happening that there will be a plane passing through this one, and also there will be a plane passing through this portion, that is from in between. Second will be that for this one you will be having symmetry element like this, that is it will be passing through this plane. And the third one there will be no symmetry element, as a result it will show enantiomeric activity, and we are going to get a mirror image which is not superimposable to it. Next we are going to deal with another one where it is MAB, that is it is non-symmetric bidentate ligand and CD. So here also you are getting two types where you are keeping the AB trans to each other and one will be cis to each other. So here you can see that they are cis to each other, and in this case it is trans to each other. Next one we are seeing MAA, that is symmetric bidentate ligand, and B and C. So here you can see one will be cis, one will be trans. So in case of cis you are not having any symmetry element, whereas in case of trans you will be having a plane passing through this. As a result it will divide this two. So our cis one will exhibit enantiomeric activity to produce a mirror image which is non-superimposable. Now the next one is MAB whole twice D2. Take the three components A, B and D. First we are going to keep cis for AB, and for D we will take it trans. So our first one will be this one. So A is cis to A, B is cis to B, whereas DD are trans. Next one we are going to keep all these trans to each other. So A will come here and B will come here. As a result we get trans, trans, trans. Next case we are going to keep our A and D cis to each other, whereas our B will be trans to each other. So this is the one. Next we are going to keep our A trans to each other, whereas the other two, that is B and D, will be cis to each other. Next one is keeping all the A, B and D in cis position. So let us find out the symmetry element first. So here you can see a symmetry element will pass through this. So this is our sigma plane, As a result, this will be optically inactive. Next one also we are going to see a plane passing through this. So this is also optically inactive. But the other three, there is no sigma plane, no I. So we can conclude that they will show optical activity. So the other three will have a pair of enantiomers, and those are mirror images which are non-superimposable. Next one is we are having MAA B2 CD. In this case you are having three isomers where you can see BB is trans to each other, BD, that is B and D are trans to each other, and C and D are trans to each other. We are keeping AA in a fixed position. Now we are going to shift for MAA whole thrice. So in this case what happens is only one possibility, which is this one, is possible, and it does not have any symmetry element present, as a result of which we can conclude that it is having an enantiomeric pair. So these are the two mirror images of each other which are non-superimposable. Now we are going to see our next one, that is MAB whole thrice. So here also, since there is a question of AB whole thrice, it was just like MA3 B3. So here you are going to see FAC isomer and MER isomer. So these are the FAC isomer and MER isomer. Again you can consider that this is present in a triangle vertex. Similarly this is present in a triangle vertex, and replace any of the vertices with this one, another functional group or another ligand, you are going to get the meridional isomer. But in this case there is no sigma plane or I present. As a result, both of these are exhibiting optical activity, and we obtain mirror images which are non-superimposable. Next, our one is this one, where you can see that there is presence of symmetric tridentate ligand. So di-N is also a symmetric tridentate ligand, we have already seen. If you have not watched the video, I will give the link in the description box as well as the I button present above this video. So here also you can get a FAC isomer and a MER isomer, but in this case you will get the symmetry elements. That is, for this one you are having I. For the facial isomer, that is, if you consider this triangle and if you consider this triangle, so they are equidistant from the center, and for this one you are having a sigma plane passing through here. So these both of them are not optically active. The last one, where you can see that there is symmetric hexadentate ligand EDTA. In this case one of the isomer is this one, and this will exhibit optical activity as there is no symmetry element present, and we can say that it will have a pair of it as a mirror image, and so these are the enantiomers which is formed by symmetric hexadentate ligand. So this was the today's topic of discussion. Hope this was helpful. Thank you for watching. Do not forget to like, share, subscribe and comment.